Welcome to podcast on Chapter 12, the first part of Lecture 2, which covers the Heck reaction and the Alkene Metathesis reaction. Here you can see a forest in autumn. And the next slide has a quote. Science can be created only by those who are thoroughly imbued with the aspiration toward truth and understanding. This source of feeling, however, springs from the sphere of religion. The situation may be expressed by an image. Science without religion is lame. Religion without science is blind. Albert Einstein said that. So let's get back into our discussion of coupling reactions. Another coupling reaction we want to look at is a palladium-catalyzed coupling reaction known as the Heck reaction that's displayed on this slide. Two examples of it. The catalyst in these reactions is a palladium transition metal. As you can see here, the Heck reaction couples an aryl or benzyl or vinyl halide or a triflate that I'll mention and explain just in a second, with an alkene in a basic solution. So here's the catalyst, the palladium tetratriphenylphosphine, and this is the base in the reaction. And this is the halide, of course, an aryl halide, and this is the alkene. And here is the product. This catalyst, PPH3,4, is tetratriphenylphosphine. Of course, the PPH3 is the triphenylphosphine, and there's 4 of them surrounding the palladium atom. Now, Heck was a great chemist, and in a minute I'm going to read an article for you about him and the fact that he, along with some other organic chemists, won the Nobel Prize in Chemistry for developing this particular type of coupling reaction. You'll notice that we're combining the halide with the alkene, and the alkene structure is replacing the bromine in both of these examples. And the OTF is a very good leaving group. And it is a tri structure of fluorine atom on the oxygen. Actually, the OTF is the oxygen atom bonded to the benzene ring, and next it's bonded to a sulfur that is double bonded to 2 oxygens each, then a carbon trifluorine moiety that makes up this very good leaving group. So you can see that we combine these 2 compounds, the halide and the alkene, forming a larger molecule. Notice that around this double bond right here, this one that now comes into this molecule, the product is trans. I'd like to read to you this article about Dr. Heck. It goes like this. This was published in October 2010, the New York Associated Press. A method for building complex molecules has paid off by helping to fight cancer, protect crops, and make electronic devices, and now it has earned its developers a Nobel Prize. 3 men, 2 Japanese scientists and an American researcher, designed the technique to bind together carbon atoms, a key step in assembling the skeletons of organic compounds used in medicine, agriculture, and electronics. Their work in the 1960s and 1970s provided one of the most sophisticated tools available to chemists today and vastly improved the possibilities for chemists to create sophisticated chemicals, the Nobel Committee said. The winners are Richard Heck, 79, a professor emeritus at the University of Delaware, now living in the Philippines, and Ichi Negishi, 75, a chemistry professor at Purdue University in West Lafayette, Indiana, and Akira Suzuki, 80, a retired professor from Kokodio University in Sapporo, Japan. Carbon atoms are normally shy about pairing up. The winning approach was to use atoms of the metal palladium, kind of like a singles bar, a place where pairs of carbon atoms are jammed together and encouraged to bond. This idea, called palladium-catalyzed cross-coupling, was easier to do than previous methods. Heck published his initial work in 1968 and an improved method in 1972. In 1977, Negishi developed a variant of the approach, and 2 years later, Suzuki developed another. It's a nice thing to have, but I don't think this is going to change my life. I'm too old, Heck told the Associated Press. So let's look further at the Heck reaction, and in particular the mechanism of the reaction. And you can see on this slide, the top reaction that's shown is the overall reaction, where we've taken a real halide and we're reacting it with an alkene in the presence of the palladium catalyst with a base in the reaction. And we form this new product that you can see here. There's 4 steps in the Heck mechanism of the Heck reaction. You do not need to necessarily memorize all of the steps, but you do need to know the overall reaction. The first step is the insertion of a palladium atom between the carbon and the halogen. As you can see here, we're going to place it between those two. It's similar in the idea of like magnesium getting between the organic component and the halogen in the Grignard reagent, as well as like copper getting between the organic component and the lithium in the Gilman reagent that we've already seen. By the way, this palladium oxidation state is 0, and the palladium in the newly formed complex here is palladium 2. So let's go on to the next slide that shows the second and third steps. Here is the pi complex formation. You can see this is the product from the first step. Here's the alkene, and we find the or the pi complex, as it's called, being formed. Reaction bond being formed between palladium and one of the sp2 carbons, indicated by this dashed line as it's being formed. Then insertion occurs when this bond is finally made, and we have a new carbon-carbon bond between the ring, and a carbon-palladium bond is formed in the sigma complex. So that's the second step. And here's the fourth step. That was the second and third step. This is the fourth step, called elimination. A hydrogen is removed and the palladium halogen bond, or the palladium halogen complex, is eliminated, kind of like a leaving group. And again, we will have trans stereochemistry because of the stability of all of this versus this part of the molecule. And again, this is the product from the third step. And down here is just showing the regeneration of the catalyst, the palladium catalyst. This is palladium 2. This is palladium with a 0 as oxidative state. This is sometimes called oxidative addition to bromobenzene. Okay, the Heck reaction couples a vanillic and an arylic halide with an alkene. And here we have the Heck reaction being coupled, the coupling of a vanillic or an aryl benzene halide with an alkene in the presence of a base. Again, there's the base, and here's the palladium catalyst. This happens to be triethylamine, and PDL2 is the palladium catalyst. Like Suzuki, this reaction is actually a substitution reaction. The R group of the halide, right here, replaces a vanillic hydrogen of the alkene. And here's the vanillic hydrogen bonded right to the sp2 carbon. If there is a substituent attached to the alkene, such as Z, as you can see here, the R group will be trans to that substituent in the product. Notice that the new carbon-carbon bond joins two sp2 carbons, this one and this one. Here's another display showing the mechanism all on one slide. The first step is, as we saw earlier, is an oxidative addition. Palladium is inserted between the carbon and the halogen, right here. R is a nucleophile. It adds to the sp2 carbon of the alkene, and the electrons of the pi bond add to the palladium, which you can see here. And of course, this is syn reaction from one side of the double bond. Next, an intramolecular elimination reaction occurs. A hydride ion is transferred to palladium, and the electrons of the palladium-carbon bond form the pi bond. Reductive elimination regenerates the catalyst and forms HBr, which you can see here. Triethylamine reacts with HBr to prevent it from adding to the alkene. The catalyst can now react with another molecule of the alkyl halide. The nucleophilic R group can add to either sp2 carbon of the alkene. This slide illustrates why high yields are obtained if the Z is an electron withdrawing group. Now notice you might want to draw a line right between these two. This is one example, here's a second example. And the oxygen, of course, in this molecule is the electron withdrawing group, and this group here, the carbon triple bonded nitrogen, is an electron withdrawing group to the nitrogen. The nucleophilic R group can add to either sp2 carbons of the alkene. The reaction will lead to a high yield of a single product only in the following situations. 1, if the alkene is symmetrical. 2, if one of the sp2 carbons is sterically hindered to nucleophilic attack. And 3rd, if one of the sp2 carbons is bonded to a group that can withdraw electrons by resonance, causing the other sp2 carbon to have a partial positive charge that will make it more susceptible to nucleophilic attack. This 3rd situation exists when Z is an electron withdrawing group, as illustrated on this slide. Notice these are resonance contributors shown with this double-headed arrow. These two examples show how the electron withdrawing group makes the carbon more electrophilic, resulting in a positive charge, as you can see in that resonance contributor and also in this one over here on the left. Now let's shift gears a little bit here and talk about alkene metathesis. So in alkene metathesis, which is also called olefin metathesis, it's a reaction that breaks the strongest bond in an alkene and then rejoins the fragments. When the fragments are joined, each new double bond is formed between two sp2 carbons that were not previously bonded. Metathesis is a Greek word that means transposition. In this slide here, you can see two new alkene products are formed, 1 and 2. The double bond breaks in each of these cases, and the fragments are rejoined, and you can see these two and these two are going to reform to form the two products. Each new double bond is formed between two sp2 carbons that were not previously joined. So alkene metathesis is attaching sp2 carbons to form new alkenes. And here is another example. If the fragments are joined as shown in this slide, but the second alkene molecule is turned around from the one on the previous slide, then the starting material is actually reformed, as you can see, looking at these two reactants and now looking at these two products. The reformed starting material can undergo another round of metathesis. Terminal alkenes give the best yield of a single alkene product because one of the new alkene products will be an ethene, as we'll see in a minute. Ethene is a gas that is easily removed from the reaction mixture. This will shift the equilibrium that exists between the two pathways for joining the fragments toward the pathway that will form ethene and the other new alkene. Here are some more examples of the metathesis reaction. As you can see in the top example, two different alkenes can be used to start as starting materials for the metathesis. We have actually 4 carbons in this reactant, 6 in this one, and then we're going to make 2 molecules of the product, which will yield, there's 5 carbons in each for a total of 10. So we still have alkene products in both of these examples. In the bottom example, alkynes can also undergo metathesis. The preferred catalyst for alkene metathesis is known as the Chirac catalyst. Catalyst that contains molybdenum or tungsten as the transition metal. As you can see here, we got a 4-carbon reactant and products that are 6 carbons and 2 carbons. So there's 2 molecules of this. You might want to write a 2 right in front of this reactant because there's 2 of those that will undergo metathesis and form these 2 products. And here is the alkene metathesis catalyst, the Grubbs catalyst. Alkene metathesis require a transition metal catalyst, the Grubbs catalyst. If it does not affect other functional groups that might be in the starting material, many different alkenes can undergo metathesis. The Grubbs catalyst, which contains ruthenium, are the most useful. The ligands, illustrated by L in the Grubbs catalyst, have undergone changes in each of the different generations of the Grubbs catalyst as it's been developed over the years. So the L, or ligands, can vary in different kinds of Grubbs catalyst, although they're still called the Grubbs catalyst. And if E and Z isomers are possible for the products of metathesis, both will be formed. As you can see here, we could form E or Z depending on where these ethyl groups will reside in relation to the double bond. And obviously this double bond here is broken and we form these 2 new products. Notice this is the ethene, which drives the reaction to the right because it's a gas. And here is another example. As we saw earlier, metathesis can also be done using 2 different alkenes as the starting material. And of course we have 2 different alkenes here, and we break both these double bonds. We can form 2 molecules of the product that's shown. We can also undergo ring closing metathesis, where the alkene is, there's 2 double bonds in the same molecule. So ring closure will occur, as you can see that's happened right here, plus the production of ethene. And we could go through a detailed mechanism for the alkene metathesis of alkenes. As you can see here, there's phase 1 is on this slide, and phase 2 is on the second slide. Phase 1 is the Grubb catalyst. An alkene will undergo a 2+2 cycloaddition reaction that's displayed here. The first phase creates 2 intermediates, 1 and 2, as you can see marked here. Each intermediate has the metal atom of the catalyst in place of a group that was attached to the double bond at the start of the starting alkene. And in this case, the metal bonds to the more substituted sp2 carbon of the alkene, whereas in this case, the metal bonds to the less substituted sp2 carbon of the alkene. Of course, it can go either way, and this is the results, 1 and 2, that can occur. So we have 2 different metallocyclobutane intermediates because the metal can bond to either sp2 carbon of the alkene, and each of the metallocyclobutane intermediates can undergo a ring opening, which are these 2 steps right here, reaction, ring opening, and 2 metal containing intermediates are formed, 1 and 2. And the second phase is illustrated on this slide, which is the metal containing intermediates reacting with the starting alkene to form a new alkenes, or to form new alkenes. In this case right here, illustrated both of these. Each metal containing intermediate undergoes a 2+2 cycloaddition reaction to form the metallocyclobutane, then undergoes a ring opening to form the other metal containing intermediate and a new alkene. This is the new alkene. Here's the metal-containing intermediate. So metal-containing intermediate 1 reacts to form, there it is 1, reacts to form metal-containing intermediate 2, and metal-containing intermediate 2 here reacts to form metal-containing intermediate 1, as illustrated on this part of the reaction. So in the second phase, each intermediate reacts with the starting material to form a new alkene and the other metal-containing intermediate. And the last slide that we want to look at in this section is illustrating alkyne metathesis. The preferred catalyst for alkyne metathesis is the Chirac catalyst, a catalyst that contains molybdenum or tungsten again. And you can see, you might put a 2 in front of this molecule. There's 2 molecules of this 4-carbon alkyne that will form a 6-carbon product plus a 2-carbon for a total of 8. And 2 of these, 2 times 4 is 8. You can see that the triple bond, a double bond within that is broken, and we end up with these 2 products. Okay, that concludes part 1.